Morning everyone, Vecko here, and today we are going to take a look at 17 integrals. So these integrals, they're pretty pretty involved. So we've got trigonometric substitutions, so that's the one over here. This looks like some substitution of some sort, partial fractions, and yeah, all of that. So the document here is available in the description on a Google Drive, and yeah, play along if you want, or just sit back, relax, and I'll go through all the working to these 17 integrals. And I'll make this working as comprehensive as possible, so you should be able to follow along if you know how to integrate. So we'll go through all these techniques. So yeah, either pause the video and give these integrals a shot, but otherwise, let's get started. So sorry for the poor lighting. Yeah, my room's a bit dark, and if I turn on the light, it'll be flickering. So yeah, we'll just have to make do. So first thing we need to just sort out is some trigonometric identities. So we have sine squared x plus cos squared x equals 1. Then we have we'll just include this. I don't think we actually use this, but we'll include it anyway, just for the fun of it. Then we also have the cos double angle identity. We also have up here tan squared x plus 1 equals secant squared x. Then we also have 1 plus cotangent squared x equals cosec squared x up in the top right. Then we also, for the cosine double angle, we have x minus sine squared x, 2 cos squared x minus 1, and 1 minus 2 sine squared x. And then also we have the product formulas for sine x cos y is equal to a half sine x plus y plus sine x minus y sine. I'll probably just cut this out. And cos x cos y equals half cos x plus y plus cos x minus y. Okay, so those are all the formulas that we're going to be needing, and by using a combination of these and some substitutions and some other methods, we'll be able to get all of these integrals done. So the first integral we have, number 1, I hope you guys can see that, is the integral from negative 1 to 1 of the square root of 4 minus x squared with respect to x. So how to get started with this is, well, we need to eliminate this square root over here. So the way we can do that is by if we make this equal to 1 minus cosine squared x, well, that's just equal to sine squared x because of the identities, because of the trigonometric identity. So if we can get that equal to sine squared x, then we can just take the square root of sine x. So, well, what would, rather than do that, I just like substituting in sine instead. So it'll be square root of cos squared x. Okay. So what we'd do is we'd have x equals 2 sine u, right? Then we differentiate that. So dx du equals 2 cos u. hence dx equals 2 cos u du. Okay, so then this would go to the integral, and well, over here we'll rearrange this in order for u. So u equals inverse sine x on 2. So here we just divide both sides by u and then take divide both sides by 2 and then take the inverse. So then we have u equals inverse sine x on 2. So since these bounds here are x, we need to find those bounds in terms of u, right? Because we're changing the variable. So the way we'd do that is just substitute a -1 into this expression over here. So we'd have inverse sine of -1/2, which is just negative pi on 6. And then inverse sine of 1/2, which is just pi on 6. So now we've changed our bounds. We can go 4 minus, substitute that in for x, 4 sine squared u times this over here, 2 cos u du. So we have here the square root of 4, 1 minus sine squared u times 2 cos u du, to go from, yeah, keep our bounds the same. So that would, and then we just substitute that in for cos squared x. So we end up with cos u times 2 cos u du, which is just, so that simplifies down to 4 cos squared u du. So the way we'd integrate this now is by using the double angle identity. The double angle identity since cos 2x equals 2 cos squared u, 2 cos squared x, minus 1, therefore cos squared x equals cos 2x plus 1 on 2. So we just substitute that in, getting hence equaling pi on 6 to negative pi on 6 cos then we just integrate that, which is pretty straightforward. Using chain rule, that would go to a half. Sorry, this is a u over here. Cos 2u plus u evaluated from pi on 6 to negative pi on 6 equaling, well, cos of pi on 3 is just a half, so that's a quarter, plus pi on 6. And then, so this goes to sine, big derp. So that'll be a half sine pi on 3, negative half sine pi on 3, and then that would be root 3 on 4, right? Because a half times root 3 on 2, plus pi on 6, and then just do it for the other side as well. So that'd be minus negative a half times negative root 3 on 2, which would just be positive root 3 on 4 minus pi on 6. Which equals root 3 on 2 plus pi on 3 times 2, which equals root 3 plus 2 pi on 3. Done. So now on to the next one. Move on to number 2. So here we have the integral of x squared root x plus 4 dx. Now here, so there's no real way that we can get rid of this square root by using a trigonometric substitution, because there's no x squared term in there. But if we think about it, we can, in order to eliminate this square root, we could just substitute in x plus 4 equals u, because by doing that, let's first differentiate this. Du dx equals 1. Therefore, we don't need to. We can just change that to du without having to times it by anything. And also, u equals x minus 4. Sorry. u minus 4 equals x. Sorry, it's a bit early. Hence, we can just do, well, u minus 4 equals x, so we can do u minus 4 squared times the square root of u dx. We can just expand this out. So we have u squared minus 8u plus 16, u square root of u, that goes to du, sorry. And we can just expand all this out to u to the 2.5 minus 8u to the 1.5 plus 16u to the 0.5 du. Now just simple integration. So that would be 1 on 3.5 u to the, bit unorthodox my working, but 8 on 2.5 u to the 2.5 plus 16 on 1.5 u to the 1.5. So if we think about, now we just substitute, we need to get in terms of x again, so we need to get rid of these u's. Well, we just substitute that in again. So I'm just going to double each of the numerators and denominators to get these all in integers, because you don't fractions. X plus 4 to the 3.5 minus 16 on 5 to the x plus 4 to 2.5 plus 32 on 3 u to the 1.5 plus our constants of integration. Third one, let's go. So our third one is this one over here. The integral of 3x minus 4 on x minus 3 x plus 2 dx. So if we look here, well, this the denominator is of order 2, so the highest term there is an x squared, and the highest term of the numerator is an x. So since the numerator is of less order than the denominator, we know it's a proper fraction, so we don't need to do any simplification. So that here would be equal to, so let's do our partial fraction decomposition. That's just equal to a divided by x minus 3 plus b on x plus 2. So then 3x minus 4, if we times both sides by x minus 3 x plus 2, if we times a by x minus 3 x plus 2, the x minus 3 would cancel out, and all we'd have is an x plus 200 on top. And then the opposite would happen for b, which is an x minus 3 there. Now, the easiest way to do this would just be substitute in a value. So we'd substitute in -2, so that a cancels. So 3 times -2, so that'd be -10 equals -5b. Hence b equals a half. And now if we just think here, well, yeah, we can just substitute in x equals 3 now to get 9 minus 4, which is just 5, equaling 5a. Hence a equals 1. So now we bring those back in here. We have a equals 1, b equals 1/2, right? And now we can just evaluate our integral to be dx. Now that's just logarithms. So that'll be natural log of x minus 3. You can put your absolute signs in there if you want. Plus half logarithm x plus 2 plus c. So don't forget your constant of integration. So that just go partial fractions and then evaluate using a logarithm. Okay. Next one would be, get mine. Number 4 is the integration of sine to the 5x cos to the 4x. Now, if these, if I was nice and if these powers were less, so if this was sine to 3x cos to 4x, it would be easier. But we'll just work with this anyway. So if you have an odd and an even power up here, what you'd need to do is use the this identity over here. Sine squared x plus cos squared x equals 1. If both of these were even, then you'd use the cosine identity to get rid of all the even powers and just get in terms of cos 2x. Okay. So let's use the identity. So therefore, well, eventually we want to get everything in terms of sine x cos n to the power of nx, so that we can use the chain rule to integrate. So we need to get everything in terms of 1 minus cos. So if we substitute that into here, we'll be good. So if we have sine to the 4x sine x cos to the 4x. So now we can do 1 minus cos squared x to the power of 2 sine x cos to the 4x dx. Meaning that goes to 1 minus 2 cos squared x plus cos 4x sine x cos 4x dx. We can expand that all out. It is a bit nasty. Sine x cos 4x minus 2 sine x cos 6x plus sine x cos 8x. That's all with respect to x. And then that evaluates to, well, the integration of sine x. So the derivative of cos x is negative sine x, so we need to get a negative factor in front of all of these. So negative 1 on 5 cos 5x. So if we differentiate that, the 5 would come out to the front using chain rule. Decrease the power by 1, times it by the derivative of cos squared x, cos x, so that would go, if we differentiated that, would go to, so the 5 would come down, so I go to negative 1 on 5 times negative sine x times that decreased by 1, so that would be cos to the power of 4x. So hopefully you can see that that simplifies down to sine x cos 4x at the end of it. Okay. So that's all good. Oh, yeah, sorry. I really need to work on my framing. So we can hence bring all of these down. Minus 1 on 9 cos 9x plus c. So this is our final answer over here. Negative a fifth cos to the power 5x plus 2 on 7 cos to the 7x minus 1 on 9 cos to the 9x plus c. Okay. Now let's go on to the next question, question 5, which is the integral of x to the power of 3 square root of 1 of 2 minus x squared dx. So we want to get rid of the thing on the numerator over here. So how do we go about doing that? Well, so we'd end up using the substitution x equals root 2 sine u, right? Because if we squared this, that will give our factor of 2, which we need here, and the sine squared u. So if we differentiate this as well, dx du equals root 2 cos u. Hence dx equals root 2 cos u du. So we bring that and we substitute it in. So root 2 sine u to the power 3 on 2 minus 2 sine squared u times root 2 cos u du. So that would go to 2 root 2 sine cubed u on root 2 cos u times root 2 cos u. So those would cancel out. So we just have the integral of 2 root 2 sine cubed u du, and we substitute in like before. We substitute in 1 minus cos squared u in place for sine squared u. Again, and then we expand and simplify. Sine u minus 2 root 2 sine u cos squared u du. Hence that's just integration of sine u is negative cos u. So that'd be 2 root 2 cos u. Then the same over here. 2 on 3, 2 root 2 on 3 cos cubed u plus c. Now we're not done. So yeah, over here, differentiate that. 3 comes out front, times it by cos u, so you end up getting negative 2 root 2 sine u cos squared u again. So we aren't finished yet because we still have a cos u term out here. Now we can go up here and say, well, u equals inverse sine of x on root 2, and then we can sub that in, and then we end up having cosines of inverse sines, and it just looks messy. Well, if we look up here, what does this over here actually mean? So if we get that and we say sine u equals x on root 2, well, sine is just opposite over hypotenuse, isn't it? So if we draw a triangle, right angle triangle, this is u, opposite over hypotenuse. This is the triangle it's referencing, right? Well, opposite over hypotenuse, if we square this, if we do our Pythag, we take the square, this side length would be this squared minus so this squared minus this is the square root of this squared minus this squared, right? Square root of c squared minus b squared. So then we end up having 2 minus x squared on the bottom there, which is this over here, right? So if we look down here, negative 2 root 2, cos u is just adjacent over hypotenuse. So that's just adjacent is root 2 minus x squared, like so. On root 2, and then plus 2 root 2 on 3. So that's to the power of 3 plus c, and we can simplify this down a bit to get negative 2. Oh, let me just use negative 2 minus x squared to the power of 0.5 plus 2 on 3, 2 minus x squared to the power of 1.5 plus c, and we're done. That is the answer for question 5. Oh, sorry, you can see that last bit. I've just been using, I don't like square root signs, so we're just using decimal powers. The next question is question, what number? Question 6. Oh, everything's blue. Okay. Question 6 there, which is the integral from x squared 1 minus x squared dx. Now, if we want to get rid of this root sign, so what we can just do is substitute in x equals sine u, and if we differentiate that, we get cos u. So our factor that we need to multiply in is cos u du, and if we go u equals inverse sine x, so now we can work out our bounds in terms of u. So inverse sine of 1 is just pi on 2, inverse sine of 0 is just 0. So those are our new bounds, and we'll have sine squared u out front, square root of 1 minus sine squared u times cos u du. Well, this is just cos u over here, so we can get that down to sine squared u cos squared u du. Now, this is where our double angle identity from earlier comes in. If I can find it, that is. There we go. That's where these identities will come in. So if we, by using those, we get it from pi on to 0. Sine squared u is just cos 2u, so 1 minus cos 2u on 2. So yeah, we get some brackets there to neaten it up a bit, times cos 2u plus 1 on 2, right? So if I rewrite this a tiny bit, just give me a sec. 1 minus cos 2u, 1 plus cos 2u, and we just, so a half times a half is a quarter, so we'll just add a factor of a quarter outside. Just draw that out. You can hopefully see that this is just difference of perfect squares. So that would be 1 minus cos 2u plus cos 2u plus, minus cos squared 2u du. So those will just cancel out. what we're left with is a quarter integral pi on 2 to 0 of 1 minus cos squared 2u. Now we can just do this again. Since we know that cos squared 2u is equal to using our double angle identity, 1 plus cos 2 times 2u, which is 4u, on 2. So 1 minus a half minus half cos 4u du. So that's just the integration of a half. So we'll do, so that's just half u minus 1 on 8 cos, sine 4u, evaluated from pi on 2 to 0, equaling 1 on 4 times half times pi on 2. Well, sine of 2 pi is just 0, so that's just minus 0, and then minus 0 since we're subbing that in over here. So that is our low bound now, which we're working with. Sub 0 into there, so that's just minus 0, and then that remains at 0 for sine of 4u. So hence we have a half times pi on, so that's just pi on 16. So it simplifies down nicely. So next up, we have the integral. So number 7, the integral of sine 4x sine 5x dx. Now here we can just use our products formula over here. So we have sine x sine y over here. So if we treat 4x as x, so if we treat 4x as and slot that in there, and 5x and slot it in for y, what we can do is say that this is equal to a half cos of, well, 4x, so that's negative x, right, minus cos of x plus y, which would be 9x, right? So that is equivalent using that formula. Now we can put that aside and just work with that. So draw the half out to the front, because why not? Integration of cos negative x. Well, cos negative x is the same as cos x. So we can just say the integration of cos x, which is sine x. Because if we look at the unit circle, if that's x, that's negative x over here. Well, these two, they still reach the same points horizontally along the axes. So those are the same value. So we can just say that's sine x minus 1 on 9 sine 9x, no integral sign there, right? So then we can have half sine x minus 1 on 18 sine 9x plus an arbitrary constant of integration, c. On to the next question. Let's see if I can squeeze it in here. The integral of x squared x plus 4, which I think we already did. So that's not our next question. I don't know how that cropped up twice. Oh well. Question 9. I'll redact that. Yeah, okay. I'll see what I do with that. X plus e to the x squared. So it looks like this is only 16 integrals. Oh well. Our 17th integral can just be, so in place for a's, we'll do the integral of e to the x dx is e to the x plus c. There we go, 17 integrals. I don't have to change the title. Question 9. Question 9. So this integral over here, well, we can't do anything with chain rule because there's the factor out the front is just a constant. It's not the derivative of what's inside the brackets. But nicely for us, it's just to the power of 2. So what we can do is just expand this. So we have x squared plus 2x x plus e to the 2x. So e to the x squared is just e to the 2x. So if we integrate with respect to x, well, this one is a bit problematic, but what we can do, let's just work with this for a second. The integral of 2x ex dx, let's just do this integration by parts. So let's say u equals 2x, therefore du equals 2 dx. And let's the integral of the derivative of v to be e to the x. So therefore v is just e to the x, right? So we do this integration by parts. We know that this is equal to uv minus the integral of v du equal to 2x e to the x minus the integral of 2e to the x, which is just 2e to the x. The integral of 2, so the integral of 2e to the x, so the integral of 2e to the x, hopefully you can see that just 2e to the x. Okay, so this is our integral for this one over here. So now we can just plug that in. So the integral of x squared plus e to the 2x plus 2x e to the x minus 2e to the x. So we still need to evaluate this integral over here, so it's a bit messy. That is a 2x. So that's our first integral over here. And this is the integral we just evaluated. So we still need to integrate this, which isn't too difficult. And now we just do the rest. And then we add our constant at the end. And if I am to check my answers, that is correct. Yeah, I double checked all my answers using Wolfram Alpha. So my working is correct. I hope. So now looking at question 10. Yep, question 10. We have a double integral now. So the integral from 5 to 8. And the integral from 0 to 4. Of x e to the xy dx dy. Now if we think about this, if we think about what this integral represents, so this is a double integral, so this is basically the volume underneath this surface over this region defined in the xy plane. So if we have the xy plane over here, the integral from 0 to 4 dx, so that's from 0 to 4 over there, the integral from 5 to 8 along the y-axis, so it's that region over there that we're integrating over. Now the problem with integrating this with respect to x first is that, well, we already have an x term out front. So if we integrate with respect to y, we can treat x as a constant, and then that just gets slotted back into the exponent. Another way we could do it is by using integration by parts, but I'd like to change your bounds, so we'll change the bounds instead. But if you want to give this a shot using integration by parts. So now we have the integral. So if we want to change the bounds, well, we'll integrate with respect to y first. So we integrate from 5 to 8. So second, we'll do 0 to 4. First, we'll do 5 to 8, x e to the xy, dy first, and then dx. Now we can do this. E to the xy dx. So if we differentiate this with respect to y, the x will come out front, which is exactly what we want. So now we just integrate this with respect to x, treating y as a constant, and we get, oh sorry, we need to, my bad. Given that y equals 8 and from y equals 5 to y equals 8 dx, so the integral from 0 to 4 of e to the 8y minus e to the 5y with respect to x. So now we just integrate that. Sorry, I'm derping very hard today. So that would just be 1 on 8 e to the 8x minus 1 on 5 e to the 5x, evaluated from x equals 4 to x equals 0. So we have 1 on 8 e to the 32 minus 1 on 5 e to the 20 minus 1 on 8 minus 1 on 5. That simplifies down to that. So that's our double integral. Oops, I think that was yeah, that was question 10. I thought I skipped ahead for a second. Yep, question 10. Now on to question 11. The integral of 1 over x root x squared plus 1 dx. Well, that's just, so we'll just substitute in one of our other identities. So we'll let x equals tan equal tan u, because we're trying to use the identity tan squared u plus 1 equals sec squared u. So dx du is just sec squared u. Hence, we can just do that. Tan squared u plus 1 times sec squared u du. So that simplifies down to sec u du, because that goes to square root of sec squared u, which is just sec u. Sec squared u divided by sec u is just sec u. Okay? And then if we want to integrate this, I'm going to take a little bit of a shortcut, because I already know that this integral is equal to, so the integral of sec u is equal to the natural log of sec u plus tan u plus c, of course. We can't forget our plus c. So now, well, if we think about this again, with tan u being opposite over adjacent, so with x over 1, then this one over here will just be the square root of x squared plus 1, using Pythag, where this is our angle u. So, using that, we have the natural log of sec u, which is just hypotenuse over adjacent. So that's just natural log of x squared plus 1, plus tan u, which is opposite over adjacent, which is just x. Then we have a plus c at the end. So that is question 11. Pretty short one, but that's if you use if you know the integral of sec x or sec u. Okay, now on to the next one. Trying to find it. Okay. Was that? Yeah, that's number 12 now. The integral of x over x squared minus 9 with respect to x. So we let x equal 3 sine u, dx equals 3 cos u du. Hence we can just substitute that in. So 3 sine u on 9. So this is x squared minus 9, so we need to use a substitution. Substitution 3 sec u. So if it was 9 minus x squared, we'd use 3 sine u, but since it's x squared minus 9, we use 3 sec u. Because this is the identity we want to use over there. So by doing that, we can get, well, the derivative of sec u is just 3 tan u sec u. Via a formula sheet that you may have. And then go the integral of 3 sec u and the square root of 9 1 minus sec u sec squared u. So that would simplify down to 3 tan u. So that and that would cancel off. And sec u, so you'd end up with the integral of 3 sec squared u du. Well, since the derivative of tan u is sec squared u, that simplifies down to 3 tan u. And using a reference triangle, so that's u. Well, x equals 3 sec u, so x on 3, sec of u equals x on 3. Well, sec u is just hypotenuse over adjacent because it's 1 over cos. So cos it would be adjacent over hypotenuse. Sec u is hypotenuse over adjacent, which is equal to x on 3. Hence this side is equal to x squared minus 9. So tan u would just be opposite over adjacent, so it'll just be root x squared minus 9 plus c. Done. So yeah. All good. The better way to do this actually would have just been to notice that this is the integral of x squared minus 9 to the 0.5th power, negative 0.5th power, dx, and then just use chain rule from there. So you'd have x divided by 0.5, so you'd have 2x just square root of x squared minus 9 plus c. So that would have been the better way to do it, if you want to use that. So yeah, the two ways to do it. Yeah, the second way is better. So now, if we want to go to question 13, the integral of x to the 4 on 1 minus x squared dx. So the way that I'll do this is just immediately I'm gonna have negative times x to the 4 on negative 1 minus x squared. This is just to make it easier for my working. So this is logically equivalent to this, because if we expand it out, the negative signs eliminate each other. So if I take this negative sign out and then bring the other negative sign into the equation, I'm left with that, which is equivalent. So this over here, I want to simplify. So I'll factor it out. You can use long division, or you can just use this method. So I'll have x squared on top, x squared minus 1. This will be on x squared minus 1. So this will cancel out with this. Well, here we have x to the power 4 minus x squared, so we need to bring that x squared back. Because so on the numerator we have minus x squared, we need to bring that back to 0, so we have plus x squared minus 1. Well, now we have minus 1 on top, so we just have a plus 1 there. Okay, so that's fine. So these will cancel off the top, so x squared plus 1 on x squared minus 1. And this over here, bring this up. 1 on x plus 1, x minus 1 is equal to a on x plus 1 plus b x minus 1. Therefore 1 equals a x minus 1 plus b x plus 1. And simplifying this, x equals 1. Well, if we just expand this out, we have 1 equals ax plus bx plus b minus a. So b minus a equals 1. And so ax plus bx, well, we have no x terms out on this side, so we know that a equals negative b. And we also know that b minus a equals 1. So we know that b equals a plus 1. And we substitute this in, so a equals negative b, b equals negative b plus 1, 2b equals 1, b equals a half, therefore a equals negative a half. Hence we have, if we combine all of this back together, we have our original integral. Hopefully this isn't too convoluted. Equaling negative integral of x squared plus 1 plus negative a half plus a half x minus 1 dx. That is just 1 on 3x cubed plus x minus a half, the natural log of x plus 1 plus a half natural log of x minus 1. And just simplify this out, simplify this again. Add in our absolutes, because why not? And don't forget our plus c at the bottom. Now on to question 14, an amount of paper. There we go. Question 14, find the volume between the surface, this, and the xy plane over the region bounded by y equals root x, so that's over here, and y equals x squared, so that's over there. So if this is root x, this is x squared, this is the region we're trying to find. These of course intersect at 1, 1, and intersect at 0, 0. So so what we can do is our integral, since it's just a simple polynomial, it doesn't really matter which since it's a simple function, it doesn't really matter which order we do it in. So we'll do it x then y. So actually we'll do y then x. Why not? So we're integrating from y equals root x to x squared, and then for our x bounds we're doing from x equals 0 to x equals 1. So if we set up our double integrals, we have root x to x squared, 0 to 1 of 8x cubed y dy dx. So let's partially integrate this with respect to y. So that would just be 4x cubed y squared, evaluated from y equals x squared to y equals root x dx. So integral from 0 to 1 of 4x to the power of 7 minus 4x to the power of 4 dx. So that's 4 on 8 x to the 8 minus 4 on 5 x to the 5, evaluated from 1 to 0. So I'm just checking my working to make sure that I am on the right track. One sec. Yep, okay. Yep. Yeah, good thing I checked. This is from x squared to root x. My apologies. So this would be x squared to root x. Hence, those would be switched around. So you'd substitute in root x, and then you'd minus when you substitute in x squared. So hence, would have 4/5 minus 4 on 8 minus 0 minus 0, which is 0. So 4/5 minus 1 on 8 is just 27 on 40. So that is our answer. All good. So that was question 14. Now question 15. Find the length of the curve fx equals ln sec x from x equals 0 to x equals pi on 4. So if we want to find the length of a curve, we can just do the integral from a to b of getting my formula sheet. Sorry, okay, there we go, got it. 1 plus f dash of x squared dx, right? So then what we'll do is, so that's the length of it, and we have our function to be natural of sec x. Well, if we just differentiate this, we get sec, so the derivative of sec x is just, where is it? It's the mess. Sec x, derivative of that is just tan x sec x, and then that would be on the original sec x. So the sec x would cancel out, so that just equals tan x. And lucky for us, so we want to do the integral of that from 0 to 4 pi. Find the length of the curve from 0 to 4 pi of 1 plus tan squared x dx. Well, 1 plus tan squared x is just sec squared x. So we can just do that again. So that can just be sec x. So 1 plus tan squared x is sec squared x. Square root of sec squared x is sec x dx. And using that identity again, is a natural log of the integral of sec x equals the natural log of sec x plus tan x plus c, but we're doing a definite integral from pi on 4 to 0. So now, if we evaluate this, get natural log, well, pi on 4, cos of pi on 4 is root 2 on 2, therefore that'll be 2 on root 2, because it's 1 over that, plus 1, which is, if we just rationalize this, times the top and the bottom by root 2, get natural log of root 2 plus 1 to be our the final length of the curve. Almost done. Question 16. Get some more paper. Find the volume created by the region bounded by y equals e to the negative x, bounded by these curves, and the x-axis, which is just y equals 0. So if we graph this out, and find the volume when it's revolved around the x-axis. So this is just exponential decay, evaluated from 1 to 5, and the x-axis revolved around, this is a terrible error, revolved around the, yeah, that should be, there we go, that's a better error, but whatever. So that's x equals 1, x equals 5, y equals e to the negative x. So if we revolve that around, well, the formula for for volumes of evolution around the x-axis is the integral of pi f of x squared dx, which is just the integral of pi e to the negative 2x dx, which is negative pi on 2 e to the negative 2x. So that's the integral from 1 to 5. Hence, we get negative pi on 2 e to the negative 10 plus pi on 2 e to the negative 2, which equals pi on 2 e to the negative 2 minus e to the negative 10. So that's our final volume. Finally, last but definitely not least, number 17. Evaluate the double integral over the region R. So the double integral is e to the negative xy dx dy. And the region is x, y, z such that 0 is less than or equal to x, which is less than or equal to 1 on y, from y is less than. So that's our region. Well, let's draw this region actually. So this goes from, so it's like so, from 0 to 1 on y. Is that from 0 to 1 on y? Wait, one sec. Yeah, okay, so from 0 to 1 on y, so that's from the x equals 0 to 1 on y, and then y equals 1 on 2, 1 to, 1 to 2, like so. So if we, at the moment we can't do this integral, because we can't do it with respect to x. We can't do it simply with respect to x. However, we can't really change the bounds either unless we want to do two integrals. We need to split it up here. So what we can do is integration by parts. So if we get this and we say, well, let u equal x, and let the derivative of v equal e to the negative xy. Wait, do we want to do this? No, we don't. Let's, one sec. Yep, we want to do this. Yep, this will be fine. Okay, cool. So therefore, du equals dx. So that equals 1, du dx equals 1. Hence, v equals negative 1 on y to negative xy. Hence, uv is negative x on y to negative xy. What I could just do, just show you my working over here. So integration by parts, you do that times that minus the integral of that times that. So we have that over here. And then we evaluate this from 1 on y to 0. And from 0 to 1 on y, because we're integrating with respect to x first. So once we evaluate that, we can integrate with respect to y from 1 to 2. That all simplifies down to that. Then you evaluate from 1 to 2. And it simplifies down to half plus 1 on e. So yeah, that is 17 integrals, and that took way longer than I thought it would. Oh well, I hope you guys enjoyed, or at least I hope this helped you in some form or another. See ya.